Okay, so welcome back. In this module, we would see a comparative analysis amongst resistors, inductors, and capacitors. We will see how the resistors, inductors, and capacitors, when they are added in series or in parallel, what is the equivalent component. So we start first with the resistors. You can see resistor R1 and R2 are connected in series, and the equivalent resistance of this network is the sum of the individual resistors. We can also see the R1 and R2 are said to be in parallel because both ends of both the resistors are connected at the same node. R1 and R2 are connected at the same node, and this node also connected at the same node. That's why they are said to be in parallel, and therefore the R equivalent of this network is written as, with this equation, R equivalent will be equal to reciprocal of, or say 1 over the reciprocal of R1 plus the reciprocal of R2. So this is how we will calculate R equivalent of a parallel network of resistors. How about the inductors are connected in series L1 and L2? For this, we see that L equivalent is equal to L1 plus L2. And now if we compare this equation, or make sure if we put up the analogy between the inductors in series and the resistors in series, we see that the in series, both in case of resistors or inductors, your equivalent value is the sum of individual values of the resistors, and here individual values of the inductors. How about two inductors when they are connected in parallel? In this case, the L equivalent is written as 1 over L1 plus 1 over L2. So if we see this equation analogous with this equation, we see that R equivalent can be calculated by this equation, and similarly, if two inductors are parallel, you have to take the reciprocal of L1 plus reciprocal of L2. So there is this similarity between how resistors are added up in parallel and series, and how inductors are added up in parallel and series. So there is this analogy. How about our third component, that is capacitors in series? So you see the C1 and C2 are connected in series with each other. In this case, however, C equivalent will be calculated as the reciprocal of 1 over C1 plus 1 over C2. So if you compare this equation with that of the inductors in series or inductor resistors in series, that's the different equation right here. However, if you would like to see this equation with when the inductors are connected in parallel, or when with the resistors are connected in parallel, you can see the analogies. So for capacitors connected in series, the equation is similar to when the inductors are in parallel, or say when resistors are in parallel. So you can relate with this and keep this in mind. How about when capacitors are connected in parallel? So in this case, C equivalent is given as simply the sum of individual capacitors. So if you now compare this equation with that of inductors in parallel or resistors in parallel, these are different equations. Your capacitance equation does not get analogy with the resistor equations in parallel or inductors in parallel. However, if you see that capacitors in parallel, which is the sum of two capacitors, have a similar analogies when with the inductors are connected in series or the resistors are connected in series. So this is how we can see the series and parallel connections between the resistors, inductors, and the capacitors, the three passives used commonly in electronics. And to remember how they add up in series or parallel, resistors and inductors in series they have the same equation. In parallel, they have the same equations. However, the capacitors case is different. Capacitors in series have the equation which is similar to when inductors are or resistors are in parallel, and similarly capacitance in series have the equation when inductors are in series or resistors are in series. So hope you found this module useful, and if you did so, share it with others for a wider range. And till then, wish you happy learning. Stay informative, stay informed, stay tuned for more engaging content like this.